Chem I. Today we are going to move forward with our discussion of the different types of matter. As we did in Unit 12, we did gases. And in the last section we were together, we did liquids. And today we're going to obviously talk about solids. Basically, this is just going to be a walkthrough of solids and the properties of those solids, but the key is what we're going to do here today is we're going to classify all solids into 4 categories. And the biggest part of this notes section is you being able to take something and then classify it into one of those 4 categories. We give you a bunch of examples, so you should be more than prepared. There will be a quiz at the end of this week, just like all weeks. I think we're getting a better hang of what's going on. I've had more participation, people making up work they had missing. We're getting there. Okay, we have 4 weeks left, I think. I think that's correct. I don't know, I could be like way off, but 4 or 5, around in there. So I'm excited. Still, once again, I'd prefer to be in class with you, but this is where we're at, and it's gonna be good. All right, 12.4 notes, solids. Let's talk about solids in general first before we start classifying them into our 4 groups. The first thing, solid is always going to have a definite composition or a definite shape and a definite volume. Okay, you can't put a solid into a different container and have it take on the shape of that container. All right, there's some things that are kind of on the borderline of is this a solid or is this a liquid, like Jello, but that's more of like, it's getting into the weeds right now. We won't deal with that. We do have crystalline and amorphous solids. Crystalline solids are things that their molecules or their atoms arrange in a repeating pattern. Even ice is a crystalline solid because those water molecules are arranging in a repeating pattern. We've already talked about ionic compounds being crystalline solids where we have a cation and anion repeating. An amorphous solid is typically when molecules or atoms come together in a non-repetitive way, and typically that gives them interesting characteristics. Glass, wax, rubber, any plastic would be an amorphous solid, which is not a repeating pattern, and you get a lot of times, like transparency would be one of the properties of many of those things. Okay, but also the ability, like flexibility. Okay, glass not so much, but some of those other things have an ability to be flexible and resilient. All right. Density, typically speaking, would make logical sense that solids are going to be more dense than their liquid and gas counterparts. Okay, so we would expect the solid form to have the most mass per volume. The one weird one is water. And you can see here it's because of the way water crystallizes, and when it does crystallize, there's all this dead space. And that dead space reduces the overall density. And therefore, that's why when we've talked before why ice floats on top of its liquid form. And it's because of that dead space that's making it less dense. So typically speaking, solids are more dense than liquids, but water's weird. So remember that. Compression, obviously solids can't be compressed. They have a definite volume, just like liquids. So that's not a property that we usually attribute to them. And then typically with solids, we start paying attention to something called melting point, which is the temperature at which something goes from solid to liquid, obviously. And this will once again be tied to intermolecular forces. If it has strong intermolecular forces, it's going to pull together and it's going to require more heat to get those molecules to separate. So higher attractive forces, intermolecular forces, means higher melting point. There's a video link down there if you want to watch that, you can. I think it's Hank Green. It's a crash course. So feel free to watch that if you'd like. All right, so now we're shifting. Those are kind of some baseline properties. Let's look at the 4 different types. Okay, type number 1 is ionic substances. We already are familiar with these. Positive cation, negative anion. Okay, and we talked about lattice energy way back in the first semester. And that's the energy that's holding this together, which is going to be dependent on the size of the ion and the charge. If it's a really high charge, like a +3 and a -3, great attraction. They're going to pull together with a great strength. And then if the ions are larger, that'll be weaker. So in other words, if the ions are small, then it will also yield to a strong bond. Why is that? It's because if ions are small, that means they're pulling in with great force, okay? And they're making that ion tighter because of the inward attraction from the nucleus, right? So smaller ions make stronger ionic bonds. Ionic solids typically have really high melting points because they are strong bonds, anywhere from 600 to 2000 degrees Celsius. You can think of sugar and salt. Sugar is bonded covalently. Salt is a ionic bond. You can get sugar to melt in a pan. Salt, probably you can't, okay, unless you have a special burner at home, okay, an enclave, which you probably don't. Solubility, because the positive cation and anion, typically ionic solids will dissolve in water, okay? They will not dissolve in, sometimes they don't dissolve, and we call those precipitate. Typically speaking, ionic compounds are conductive if they're dissolved. So if we dissolve salt in water, because of those electrolytes, it'll conduct a current. And typically they're non-volatile. We're not going to put salt on the counter and have it evaporate because it has really strong forces that's holding it together, okay? Let me give you a bunch of examples of ionic compounds here, things we've seen before: cation, anion, cation, anion. Okay, so ionic compounds, relatively strong, and these are kind of their properties. A molecular covalent compound we've talked about before too. This is when you have two nonmetals that are bonded together covalently, all right? The intermolecular forces that are holding these together will be strong or weak depending on what type of intermolecular forces we have. Do we just have LDFs or do we have hydrogen bonding? All right, water would be an example of this. CO2, O2, N2, gases, liquids that you're familiar with. The stronger the intermolecular force, it's going to affect things like melting point. Typically they have low melting points because this bond is probably the weakest. If you think about the things I just named, N2, O2, H2O, liquids and gases, right? That means they don't have intermolecular forces that's holding them together with great strength. Solubility, they're typically insoluble in water, okay, because a lot of them are nonpolar, but they will often dissolve in nonpolar solvents. They're not conductive, but typically they are volatile if they're liquids, or some even start out in the gas phase, okay? Now, once again, that really depends on what type of intermolecular forces we have. If you look down here, sugar isn't volatile. It does not evaporate readily, all right? But water, yes. There's other liquids there, and ammonia, okay, NH3, that evaporates pretty readily. That's why you smell it. It's got a strong smell. All right, so it's because they're held together by intermolecular forces, and there's such a wide range. Some properties are demonstrating a very wide range of, yes, this will evaporate readily, or no, this won't. Okay. Network covalent solids. These are the strongest networks. This is what this is when you have covalent bonds that are repeating in a network. You are familiar with these substances. Diamonds are examples of these substances. Graphite. These have extremely high melting points because those covalent networks make it so strong. Okay, it's not being held by intermolecular forces. It's being held by intramolecular bonds. Okay, those that have to be broken. So that's why a diamond is so strong, because it has all those covalent bonds in that rigid structure. Because those bonds are so strong, it's going to be insoluble in water. It's also going to be insoluble in nonpolar solvents. Diamonds don't dissolve. Okay, you'd have to chemically react to the carbon to break them down somehow. They're not very good conductors because all the electrons are in the bonds, and they're not volatile. Okay, because they're so, once again, bonds are really, really strong. Keep in mind that network covalent solids are the strongest bonds. Look, diamond, graphite, which would be like the graphite in your pencil, SiO2, which is quartz or sand. There's only there's only 8 of these. There's only 8 that are network covalents. They are rare, they are strong, and they stay solid because of this. Okay? You can have a look down here. Carbon makes both graphite and diamond. It's just arranged in different ways. You can see how the diamond is a like three-dimensional structure, and graphite is actually layers. That's why when you write with a pencil, you see it because those layers are being peeled off. That's literally what you're doing when you write with a pencil, is you're just shaving layers off of a graphite nonpolar or network covalent solid. Okay, last one, which would be metallic substances, solids. This is when we have a cation that has electrons that are delocalizing. Okay, sometimes we say a sea of electrons. So what you have is, let's say we have a sample of titanium. We have all these titanium nuclei, and then their electrons that they have, which I believe titanium has 4 valence electrons. They will delocalize and be able to like basically travel throughout the body of all those metallic cations. This typically makes pretty strong bonds. The greater the charge of the ion, the stronger the bond, and the larger the ion, the weaker. Remember, for ions, we want small ions, which means they're strong. Metals can have a wide variety of melting points because we know that some metals, well, one metal, mercury, is already liquid. And we know that the first column metals, like potassium, have really low melting points. It's because they're large ions with a small charge. Okay? So as charge increases, the metallic bond strength increases. But we can get things like tungsten that have melting points all the way up into the 3000s. So there's just a huge range of melting points because we have a huge range of strength of metallic bonds. Solubility in water, none are soluble, but some do react with water. We know the first 2 columns react with water, and then they're not soluble in nonpolar solvents either. Obviously, metals are conductive, and it's because of that sea of electrons. Those electrons that have the ability to move throughout the body, that's what allows them to conduct. Electricity is defined as a flow of electrons. So if you have electrons free and available, like in a metal, okay, they're going to travel throughout that body, if it's a copper wire or whatever it is. And then volatility, obviously metals don't evaporate except for mercury, and that's what makes mercury dangerous. Mercury, the liquid, is not dangerous. It's when it vaporizes and then you inhale it, that's when we get problems, okay? And that's why we don't have mercury in schools anymore and things like that. Under examples, we're just giving you examples of metals, right? Just from the periodic table. Those are the ones that are going to make metallic bonds, all right? All right, so this brings us to kind of the work portion of identifying solids. The way we do this is kind of with a method here. The first question, does your solid contain a metal? And it's kind of, and if yes, go to 2, and if no, go to 3. It's kind of like a dichotomous key here. And you can see that 2 and 3 ask other questions, and we only have 4 categories of solids, okay, that we could potentially end with. So let's go ahead and start this. Right off the bat here, I'm going to have you cross out that first one. It's a tricky one. If we had more time in class, I'd explain it. It's because silicon's a metalloid and it messes everything up. We're going to ignore it. Okay? Let's stick to the basics here. All right. So, first question, NaCl, does this contain a metal? Yes, it does. So go to number 2. Number 2, does it contain a nonmetal? Yes, chlorine is a nonmetal. So therefore, this would be ionic. Okay? And that's pretty much how you use the system. Now, some of these you're going to get quicker at. Okay? This one, glucose, we got carbon, hydrogen, oxygen. Is there a metal present? None of those are a metal. So if no, go to 3. Is it one of the 8 networks? This is not one of the 8 networks. Remember, networks are super strong. Diamond, quartz. Sugar, not that strong. We can meld it. Okay? So we know that this is molecular. It's not one of the 8. Copper. Listen, you can go through the list there. Anytime you see a metal by itself, guess what? It's metallic. So right off the bat here, you should look at copper and say, that's metallic. This is potassium. That's a metal on the periodic table. That's metallic. Okay? Those are the easiest ones to label. SiO2. I would say that silicon in this way is not behaving as a metal. Okay? And then ask, is it one of the 8 networks? The answer to this question is yes. SiO2 is quartz, so this is a network covalent. You might ask yourself, well, how would I know that? You're going to have it right in front of you, okay? If you get to the point where you think it, I mean, typically if we were in class, I'd say you need to memorize those 8. But everything we do right now is online, so you don't need to memorize it. You just need to know to be wary of those 8. Diamond, graphite, silicon, silicon dioxide, germanium, red phosphorus. Okay, look, here's Bn. Guess what? If you're looking ahead, there was Bn on here. So that's a network covalent. Okay? So what that means is these two right here, they're super strong. They don't dissolve in anything. They don't melt. Okay? They melt at really, really high temperatures. Really strong bonds, covalent networks. MgO, magnesium's a cation, oxygen's an anion. That means this is ionic. Okay? So you will get better at this, kind of picking these out once you kind of learn the characteristics to identify them. Okay? One last thing here, which is a continuum of strength. All right? The weakest ones are molecular, and that should make sense because they're mostly gases and liquids. O2, H2O, CO2, NH3. The next step up is where it gets a little tricky. Ionic and metallic actually have some overlap. Both of them have melting points across the broad spectrum, and I wouldn't say that it's clearly one or the other here in this second position. You could probably mash ionic and metallic together and create like a column in the middle. And at the far end, the strongest, okay, so this is the strongest end, we've talked about this, covalent networks, diamond, quartz, sand. Those are very strong networks of covalent bonds, and they take a massive amount of heat to melt them. They don't evaporate. They don't dissolve. Okay, it's because of those strong bonds holding them together. The activity that you have in front of you is just a chart that's helping you kind of place some information about these 4 types. Your job is simply to fill it out. I'm not going to collect it. It would probably be something helpful for you when you're getting ready for the quiz, though. So it's up to you how much you think you need to review. But once again, I'm going to get the information that I need from the quiz on Friday. If it's valuable to you to do that activity, do the activity. If you can do half of it and start to see what's happening, that's fine too. But just understand that those are the questions I'm going to be asking. All right? Good job today. Have a good week. We will see you Wednesday. If you need to stop into office hours tomorrow from 1 to 2, please do so. Talk to you later.